The title of this talk is on the effect of Hubble expansion on wide binary and spiral galaxy rotation flattening during and after cosmic deceleration to acceleration crossover. Now, the focus of this talk is on the crossover itself, with less emphasis on the local universe conditions. The reason being that there are certain mathematical challenges regarding the local universe conditions, and that work is going to be addressed over the next period of time. And with that, we go to the next chart. So this chart is an introduction, which it's unusual in a presentation, but since it's a video, I think it's helpful. And we have here a quote by Einstein: "The supreme goal of all theory is to make the irreducible basic elements as simple and as few as possible without having to surrender the adequate representation of a single datum of experience." I totally agree with this. And then below that, we have another paragraph: support for anisotropic light speed and relativity physics and other subjects like quantum mechanics has been provided by the discovery of cosmic acceleration in the late 1990s. And this unexpected empirical discovery has resulted in a change at the foundation of special relativity. And here we indicate that we have as changes the enhancement / extension of Einstein's isotropic C equal constant light speed by the more empirically significant inward near infinite light speed to each spacetime point. So this is sort of a new mathematical dimension, and it encompasses a possible solution of long-standing problems like cosmic acceleration, rotation flattening within spiral galaxies, and action at a distance in quantum mechanics. So that's what's presented in this set of charts here. There is a summary of the presentation below. And with that, we go to the next chart. The chart here is optical anisotropy between two mirrors at speed beta equals v over c along positive x-axis. So we have two mirrors left and right with a single photon bouncing back and forth. And these two mirrors in baseline Einstein synchronized inertial reference frame are moving to the right at v is equal to beta c. But in the Lorentz transformed x prime frame, the two mirrors are stationary. We have x prime is equal to 0 under the left mirror, and x prime is equal to delta x prime under the right. So an important point here is that under the relativity principle with Einstein synchronization, time for a photon to go from the right mirror to the left mirror is delta x prime divided by c. But given anisotropic light speed, or light speed right to left, exceeds c, the time is reduced. And this development below derives that elapsed time of photon flight given by delta t sub r prime, x prime is equal to 0, is equal to delta x prime divided by c minus v over c squared times delta x prime. A little box above it, given near infinite inward light speed. This development here and that equation is valid for any given condition of anisotropic light speed. And below that, we have inward infinite light speed, c sub r prime, is equal to c divided by 1 minus beta, as beta goes to 1. In fact, we don't go all the way to 1. We have to come up short infinitesimally in order to retain analytic function. Now, an important point here is that this chart would not be shown today, or any of the other charts, were it not for the Hubble space expansion. It's the Hubble space expansion that gives scientific and empirical significance to the anisotropic light speed, and in particular, inward infinite light speed. Now we'll go to the next chart. This chart, supernova magnitudes, theory versus observation. And on the left-hand side, we have the derivation of pure cosmic acceleration. Call your attention to that small box. T prime is equal to T minus R over C. T prime is look-back time, physically meaningful, empirically meaningful. And then there's the development further down. resulting in the cosmic acceleration r(h)² derived. Now on the right-hand side, lower right, there's a box which shows comparison of the present theory and lambda CDM with supernova type 1a measurements, latter part of 1990. On the ordinate, we have delta m minus m, supernova magnitudes. The abscissa z is redshift. So the dashed line tends to go through the supernova data out to 0.3 leading order, but the lambda CDM tends to skirt above the data. Now we go to the next chart. This chart was presented last year, and it's updated for the meeting this year. Wide binary and spiral galaxy rotation theory versus observation. In the first box, we have at cosmic acceleration crossover, h is the Hubble parameter, equals r0 h0 divided by r, applies giving the subfield gravitation inverse radius. The h expression is plugged into the equation at the left, permitting its differentiation, and the expression for subfield gravitation. Below that, we have the derivation of the h expression. The terms on the right in this Taylor series expansion are 0 at the crossover, but remain finite in the local universe. And the remaining task is to demonstrate that these terms are negligible in the local universe. Now, on the right-hand side, we have comparison of present theory with observation. We have the Tully-Fisher relation down at the bottom, and the present theory goes through it. However, once again, we have to demonstrate that the higher order terms are negligible. So we have a valid comparison of theory with observation. Same thing is true with the wide binary plot at the top. Now we are acquiring spiral galaxy rotation data at the crossover, and this is referred to in the dotted box at the far bottom and right. Rotation flattening and the crossover epoch may show a Tully-Fisher M versus V shift, thereby enabling a critique of ASF theory. This is Sharma et al. Observational evidence of evolving dark matter profiles since Z less than equal to 1. It just came out recently, 2022. So this can provide a basis for critiquing the present theory. Now we go to the next chart. Now this chart was presented last year and it's updated for this meeting. And on the left side we have some bullets, and I'll read a couple of them. When an inward photon at near infinite light speed enters a telescope or a laboratory instrument, the same photon extends back into its emission source. And then as a result, photon wave function, this function here, at standard light speed c becomes the leading order, another function extending back at c minus much, much greater than c. Then there's two bullets down here which refer to the physics attending the near infinite light speed from the emission source into the local absorption plane. On the right side, we have in-progress developments, which pertain primarily to the crossover. At crossover, cosmic deceleration and cosmic acceleration exactly offset, resulting in inertial frames throughout the universe at the crossover, just in the coasting mode. And this condition facilitates the Lorentz transformation, but I do believe that the Lorentz transformation can be applied outside of the crossover epoch. Further down, we have the equation x underscore is equal to c minus over c times chi, where chi is cosmic distance along the wave packet. Now, chi is, of course, much, much smaller than the cosmic distance, but when we multiply that by c minus over c, it expands it. So now the wave packet, the photon, extends from the absorption plane back to its emission source. And at the bottom, we have a paragraph which pertains to the inertial frames, coasting inertial frames. They have the relativity principle, which allows us to convert from anisotropic light speed to isotropic light speed and these inertial frames. With that, we go to the final chart. Okay, the final chart, concluding notes, and the first bullet is perhaps the most important. Anisotropic light speed and near infinite inward light speed in particular is an enhancement / extension of Einstein's isotropic light speed, which extension may be considered scientific due to its greater empirical significance. So here I'm not negating Einstein's isotropic light speed. It's a special case. But when we go to anisotropic light speed, now we're going into a new dimension, and mathematical physics is more able to encompass new empirical discoveries, and that's what my work has been about. The new empirical discovery being cosmic acceleration in the late 1990s. So the rest of most of the rest of this chart gives an overview of the presentation. Down at the bottom is the conclusion, and I'll read it. Future studies will continue to address certain local universe challenges in justifying the Hubble expression h equals r0 h0 divided by r, which arises naturally in the cosmic deceleration to acceleration crossover in the derivation of a sub sf in the, again, local universe, and also seek deeper connections between near inward singular light speed and the quantum mechanical function. Thank you.